In solvent-based automotive coatings, flash-off and solvent evaporation are not passive waiting steps between application and curing. They are active rate-controlled processes that determine whether a wet film transitions into a uniform, defect-free, and durable coating, or into a system carrying hidden risks that only appear during OEM validation or in the field. Flash-off refers to the controlled period immediately after spray application, during which low and medium boiling solvents evaporate, allowing the coating to move from a sprayed liquid state toward a stable, semi-structured film. This wet-to-dry transition governs leveling, metallic flake orientation, solvent release, and surface topology, and it must occur within tightly defined windows. At the formulation level, solvent blend composition defines evaporation kinetics. Fast solvents drive early viscosity, increase, and rapid skin formation, while slower solvents maintain film mobility for leveling and orientation. The balance between these fractions determines how long the coating remains flowable and how quickly internal diffusion pathways close. Poor balance results either in premature skinning or excessive openness. At the process level, flash-off time, airflow, temperature, and humidity directly influence solvent partial pressure gradients. Increased airflow accelerates surface evaporation, while high temperature reduces solvent viscosity, but can also collapse the evaporation window. Humidity further complicates this behavior, especially in basecoats, where moisture can alter solvent activity and resin mobility. In primers, flash-off primarily controls solvent entrapment and film continuity. Insufficient flash-off traps solvent beneath the surface, leading to popping, blistering, adhesion loss, or intercoat delamination after bake. Excessive flash-off, on the other hand, increases viscosity too early, reducing leveling and increasing orange peel transfer into subsequent layers. In basecoats, flash-off is critical for metallic and effect pigment orientation. During the wet phase, flakes align under gravity, surface tension gradients, and shear relaxation. If solvent evaporation is too rapid, viscosity increases before flakes can orient properly, resulting in mottling, patchiness, and poor flop. If evaporation is too slow, flake movement continues too long, increasing flooding, striping, and color non-uniformity across complex vehicle geometries. In clearcoats, flash-off governs surface, leveling, and final texture. Early solvent loss increases yield stress, locking an orange peel. Delayed evaporation improves leveling, but raises the risk of solvent popping during bake if diffusion pathways are insufficient. Clear coats are particularly sensitive because they lack pigment to mask surface defects, making flash-off control critical for appearance metrics, such as DOI, haze, and gloss. The wet-to-dry transition represents the point where solvent loss causes a rapid increase in viscosity, transforming the film from a flow-dominated system to a diffusion-dominated one. This transition defines the final film structure. Once crossed, defects introduced earlier cannot self-heal, and any trapped solvent becomes a latent failure risk. In OEM production, variability in booth airflow, line speed, body temperature, and environmental conditions shifts flash-off behavior daily. A formulation that performs well under laboratory-controlled flash times may fail when exposed to real production variability. For this reason, OEMs define acceptance limits and process windows, not ideal conditions, and evaluate coatings for robustness rather than peak performance. Our D&I teams therefore design solvent packages to tolerate shorter and longer flash-off times, ensuring acceptable appearance, adhesion, and durability across realistic plant conditions. Flash-off is not optimized for perfection. It is engineered for stability under variability. In summary, flash-off and solvent evaporation control the entire wet-to-dry transition in solvent-based automotive coatings. They determine leveling, metallic orientation, surface texture, solvent release, and long-term durability. Mastery of flash-off behavior is essential for translating laboratory success into OEM-approved, production-stable coating systems. If you have technical questions on flash-off optimization, solvent popping, metallic control, or lab-to-line evaporation mismatches, share them in the comments for discussion in future episodes.